So my name is Jackson Marusarz. I also work at Intel with James in the Developer Products Division. Today I'm going to be talking about a performance tuning methodology that we espouse here at Intel, and it's pretty applicable. It's not just an Intel-specific thing. It talks about performance tuning at various levels in sort of your system hierarchy and where you're going to get the most bang for your buck and where to focus your time and effort. Some of the things I'll talk about will be Intel specific, and I'll try and call those out because this is the architecture track. There are specific things that we talk about for our architecture that may or may not be applicable in other architectures. So why do performance profiling? This is kind of a slide of rhetorical questions, right? We all know why we want to do performance profiling and performance tuning, especially at this particular program that we're at here today. For extreme scale computing, we can't just get the algorithms right. We have to get them high performing in order to scale to exascale and whatever the next thing is going to be. So reducing the direct compute time cost. Obviously, you're paying for hours on a machine somewhere, or you've got a grant that lets you work somewhere. Doing things more efficiently lets you get more work done in the same amount of cycles. There's a lot of indirect costs associated with having poor performance. We heard yesterday, if you reserve 32 nodes, but you only use 16 of them, you're paying for those other 16, right? So you might not think that you're not performing well, but really there's a lot of indirect costs with having poor performance. And better user or customer experience, that kind of sounds like a marketing bullet, but if you're writing a library that you want other people to use, if they try it out and their first reaction is, this thing performs terribly, even though the answer was correct, they're probably not going to pick it up again. So it's really important that you focus on performance all the way through your development cycle. And I guess this is sort of my rhetorical part of the slide. If you're not in that business, don't bother. But I think we should all, everyone in this room, be in the business of writing high-performance software. It's not enough just to get the right answer. As you're doing your software development, some of you are probably working on 20-year-old legacy codes, and some of you are starting from scratch. But performance should be something that's in your mind throughout the development cycle. Some of you may be past this design cycle and not really have the ability to think at the algorithm level. But for each level of this design cycle, don't have performance be a second-class citizen in your brain. Right? When you're designing, think about your algorithm from a performance perspective. Yes, you want the algorithm to compute the number that you need, but you also want to do it efficiently and quickly. When you're in the prototyping stage, choose performance-effective solutions and try out several of them and monitor their performance. When you're in the implementation phase, apply some performance optimizations and add that to your regular testing, right? Change things that don't affect the outcome of the algorithm, but change how the performance works. And I've got more slides on all of these various phases throughout the presentation. I've got a slide about adding performance regression tests to your application. You probably have nightly tests to make sure you didn't add any bugs to your application, right? But you should also have nightly tests to make sure you didn't slow down your application. Make sure your library didn't get much worse because of the changes that you made. And obviously, when you release, if you have the option of adding things to your application that can provide feedback as to how it's being used, you can use that information for future performance tuning. So what does this top-down hierarchy look like? Well, it is kind of arranged in a bigger to smaller order. At the very top, we've got what we call the system and doing performance tuning at the system level. This is, in your case, a large hardware cluster where there's certain things that can be changed. After you've done performance tuning at the system level, the next level is the application level. This is where you're tuning your algorithm, you're changing most of the source code to get higher performance algorithms, you're adding OpenMP, that sort of thing. And at the very bottom of the performance tuning is the processor level. This is when you're tuning for microarchitectural specific features. And as a guy from Intel, when I start talking about this, I'm going to be talking about Intel's microarchitecture and how you tune for it. Other hardware vendors with different architectures might have a different pitch for tuning for their microarchitecture. This stuff up here, a lot of it's going to be applicable across different machines. The stuff down at the bottom is going to be Intel specific. And there's a link here for a white paper that's online that's really detailed about this hierarchy and I definitely recommend everyone checks that out. It's a little bit out of date, so some of the references to different architecture features might be a few years old, but in general, it covers this really well. When it comes to performance profiling, one thing that I think a lot of people are guilty of, myself included, and probably a lot of people in this room, is not really considering using tools. I'm actually a tools guy. The group I work in develops tools for performance analysis. But as machines get more and more complicated at the hardware level, at the system level, all across the board, it's not enough to just put time statements in your code, see how long things took, and then try and tune from there, right? Performance tuning is a complicated process, and there's tools out there specifically designed to help you. So throughout this presentation, I'll hit on a lot of different tools and how they can be used at various levels to help you. At the system level, there's profilers for entire systems where you're just getting an idea of how well is my system behaving. At the application level, that's where there's a lot more tools. You have to consider what language are you developing in, what is your application doing specifically, which operating system are you on. But the reason there's so many tools here is because that's where tools developers can make money, right? There's a lot of application developers out there, and if you write a tool that targets application developers, that's where you're going to sell the most pieces of your tool. These system things up here are usually just sort of integrated into the OS. And then at the microarchitecture level, there's also some tools available for tuning. Intel has one that I'm going to talk about for Intel microarchitecture. But if you're on a different microarchitecture and you want to tune for those transistors on that chip, you're going to need some sort of tool, usually by that platform vendor or someone very close to that platform vendor, because they know exactly what's going on that chip. So just to reiterate, tools are essential for efficient performance analysis, and hopefully by the end of my two presentations, I can convince you of that. I'll say a lot about various performance issues, but I'll also say quite a bit about how you would find those with a tool, because a lot of them are not obvious. All you would say is, my program's running slowly, now what, right? Without a tool, you might not really know where to go from there. The first level I'll talk about is the system level. And this is the level sort of that's kind of tweakable by system administrators, some performance engineers, people who own the machine, that sort of thing. So how do you do performance tuning at the system level? This is really all about configuring the hardware to make sure it's taking advantage of everything that you bought and put inside of that machine. Generally, you're not targeting a specific application at this level. You're targeting, some sort of benchmark or a cross-section of benchmarks that might represent the types of jobs that would be running on your machine. So I've got a list here of a few different common benchmarks. You're probably all familiar with the stream benchmark, which just measures the, memory bandwidth. There's a lot of different flops benchmarks, linear algebra libraries out there. There's some benchmarks for your network. Intel has an MPI benchmark that's not actually for MPI performance. It also does things like memory latency and memory bandwidth for a cluster. So at this level, what you're going to be doing is you're going to be looking at sort of these high-level benchmarks and using some sort of tool to figure out whether your system is performing up to snuff, right? I've got a list of a lot of different tools here. These are all very high-level. Linux type of integrated OS, basically commands, right? And then there'll be some vendor and platform specific tools. And if you run into issues at this level, for example, your benchmarks aren't performing as well as you would think, what are the fixes? Well, often, unfortunately, the fix is to upgrade the hardware, right? If you think that your machine should be running at X and it's running at Y, sometimes you can figure out the bottleneck is the hardware and I need to upgrade it. Unfortunately, that costs money. So that's usually not an option for most of the people in this room, right, to buy a new machine. There are some other configurations that you can do. The BIOS and the OS has a lot of different configurations. There's things you can turn on related to prefetchers. NUMA, which is on multi-socket systems when you're accessing remote memory. There's various configurations in the BIOS for that. There's a lot of power settings in the BIOS that may or may not throttle the frequency of your processor to get inside of some power package. SMT like hyperthreading, that can usually be turned on and turned off in the BIOS. And if you're doing purely MPI jobs, that's something that a lot of clusters will do, is turn off hyperthreading. But if you've got OpenMP, for example, inside your MPI, you can get a lot of power out of hyperthreading. But the key takeaway from this slide, actually, after I rambled on about it, is this is often outside the capabilities of most users, right? If you're just using a machine that you rent time on, chances are you don't have the option to go into the BIOS and flip these flags. Chances are you don't have, the clout to tell them, hey, you need to buy some faster memory. So I'm not going to talk a whole lot about system tuning in my presentations, but just be aware that if you're a machine owner or someone that has the ability to change these type of things, this is the first place to look for performance tuning. Because if you can change something here that upgrades your system, you're helping out everybody that uses that system, right? You're getting performance across the board, and that's how the hierarchy is designed. What's the first place to look that's going to help the most people? And system tuning at this level is at the top of that hierarchy. So for the introduction, that's the only slide I have for the system. The application is where it gets a lot more interesting. This is where we're doing things to tune our application at various levels to get more performance. Generally, there's some expertise associated with this. You need to know something about the algorithm. So the people that would be doing this type of application tuning would be software developers, performance engineers, and domain experts. So how do you do application tuning? Well, you have to have some sort of workload selection, right? Most people are going to have some application that they work on regularly that they're trying to target for performance. And once you know what that workload is, whether it's a test suite with that application, or it's a single input, or it's a suite of applications, you want to figure out a way to get repeatable results. When you're doing performance tuning, pretty much what you're going to be doing is comparing run A with run B. And if they didn't do the same thing, then the performance comparison that you get isn't really going to be valid. So you need to figure out some way to get repeatable results. And also, when you're doing a profile, you want to make sure that you're profiling a steady state. A lot of the things I'm going to be talking about today are not things where you're going to profile 15 hours of your application, right? When you're doing a lot of different performance profiles, that can create huge amounts of data to correlate back to where the bottleneck was. So what you really want to be profiling is the steady state of your application, and then tuning that steady state, which ideally is probably repeating itself multiple times, right? If you have a loop that does 1 million iterations and it takes a whole day to do it, but it's doing relatively the same thing every time, you can just profile 1 or 2 of those iterations and get an idea of where your performance bottleneck is. The opposite of that is if you have an application that has 5 distinct function calls, A, B, C, D, and E, and you profile during a time when you're running function B, and you compare it to a profile when you're running function C, that's again not going to be a good comparison. So you need to profile while you're in some sort of steady state and compare it to another profile done in the same steady state. When you're doing this type of performance analysis, you want to define some sort of metric that's important to you. And the first thing you want to do is create a baseline. How does my application run today? So the most common metric, and my favorite and many people's favorites, is just wall clock time, right? For the same amount of work, if I look at my watch and I start it, and then when the work is done, I stop it, how long did that take, right? And things like adding parallelism will decrease the wall clock time. Things like adding vectorization can decrease the wall clock time. So probably 90% of the time, that metric matters to people. How long did it take my application to run? There's other metrics like flops if you're in some sort of benchmarking competition, frames per second if you do some sort of graphics. So you really need to know what metric is important to your application and create a baseline. So use some sort of tool, or if you have some integrated performance characteristics in your application, create a baseline today that says, here's how well I'm running. The next step in application tuning is identifying the hotspots of your application. You need to know where is your application spending time. That's what a hotspot is. Whether it's a library a function, a certain line of source code, 15 lines of source code, a loop. There can be various granularities for hotspots, but that's the most important thing to know when doing performance tuning. If you're going to spend 6 days parallelizing a for loop using OpenMP, and then that for loop was less than 1% of your overall runtime, you've pretty much wasted your time doing performance tuning. No matter how well you've tuned that for loop, if it wasn't a hotspot, you're not going to get the kickback that you expected. This really touches on what James mentioned about Amdahl's law, right? You are limited by the serial portion of your application in the case of parallelism. So you need to focus efforts on areas that are the most time, or at least the most impactful to whatever metric you are using. And the easiest way to identify the hotspots of your application is through the use of tools. You might think even using something like OProfile, that's all I use. Well, that's a tool, right? There's very few ways to get the hotspots of your application without some sort of tool, whether that's instrumenting your own code to time the various regions of it or using some sort of profiler. After you've identified the hotspots, you want to determine where is it inefficient. Is it inefficient because there's no parallelism? Is it inefficient because there's some sort of hardware bottleneck, which is often the case? What would help me in these inefficiencies? Would better algorithms help me? Would change of programming language help me? At this level of application tuning, you often require some knowledge about what the application is doing and its algorithms. When we talked about the system level up above this, those guys didn't really know what the applications that were running did. They didn't need to know, which matrices need to get multiplied together and transposed. They were just tuning at the system level. At this level, it does require some knowledge of the application and its algorithms, but hopefully, everyone in this room has some application that they work on, and they know a little bit about what's going on there. You're going to need to, know if I change this algorithm, is it going to lead to an incorrect result, and have some idea about that. Finding hotspots, which I talked about as kind of the first step in doing application tuning. There's a lot of different granularities where this could happen, and it's up to you to determine what is the important granularity for me. Is it important that I know the exact line of source code that's a hotspot, or is it just important that I know which libraries are taking up the most time? One tool that you can use to do that is OProfile. You guys might all be familiar with that. It's a very common tool. It basically has a text-based output, but it does give you the ability to use a very fine-grained timing using hardware events that I'll talk about later to get the hotspots in your application. I would say this is probably the quickest to get started with, but not necessarily the most user-friendly. Then we get into tools that provide GUIs. For example, sysprof here, you can get sort of call stack trees, which are important when doing performance analysis. Changing the granularity dynamically is also useful. I know I'm going to have a lot of screenshots of GUIs in here, and a lot of people in this room probably don't use GUIs, and that's fine. But hopefully I can convince you that tools provide so much value, and the ability to visualize your application in something other than black and white text hopefully will convince you to start looking at some other tools, right? You can sit there and look at text like this all day, and some people can interpret that quickly, and some people know exactly where to go from there. But when you're looking at a dynamic application that has, various states in it over time, it has different, different characteristics over time, a text-based, output like that can really be limiting. So hopefully you give GUIs a chance. Another tool, so this is an Intel tool here, vTune Amplifier XE, and this is the same tool that I'll be referring to when I talk about tuning for Intel Microarchitecture. This is the Intel Performance Profiling tool that has a GUI here with hotspots. In addition to just telling you where you're spending time, this is showing some additional information about how well are the other CPUs being utilized while you're doing this analysis. So that's some information about parallelism and scalability as well. Hopefully this looks a little prettier than your standard text OProfile output. Another feature of vTune, I won't plug vTune too much here because there are other tools that do this as well, but obviously I'm most familiar with our Intel tools, is the ability to look at hotspot data on the source line in addition to just at the function level. So some of you may not have seen this capability before. With these fine-grained performance analysis tools, we can actually break down time at the line of source code for your application. This works, for C++, Fortran, whatever application you're in. And people oftentimes are interested in the line of source code, but you can also look at the line of assembly code. Which exact assembly instructions am I spending the most time on? And some people find that really interesting, and some people don't care about that at all. So they'll never look at it again, and that's fine too. But just be aware that when you're doing performance tuning, you don't just have to run the application, see the wall clock time, then just kind of guess what you can do next to tune the application. By using tools, you can actually save a lot of time knowing where to focus and what to be looking for. Another kind of just quick aside that I like to use this for is if you want to know whether you're vectorizing, someone asked about whether or not you're vectorizing, you can look at the lines of assembly that were created from the lines of source code and see whether it's AVX2 instructions that are listed there, whether it's SSE instructions that are listed there, and you can know exactly what your compiler generated from the application. A lot of times, people doing hotspots analysis will just totally shore up what they thought about their application. I knew I was spending all my time here. Hotspots analysis verified that, and that's where I was going to focus anyway. But you would be surprised how many people do a hotspots analysis on their application and find quite a bit of time spent in locations they had no idea they were spending time in. They thought all of their application was spending time in this one hot loop doing all the math for their algorithm. But it turns out 15% of the time was in some I/O logging routine. And maybe they didn't even really need to do that. It's just on by default. And if you turn that off, you can get a big performance boost. And you would never know that if you just used your intuition about your algorithm to focus your attention. Right? You need to do some sort of analysis to figure out what sort of things might be going on that I would never consider. And that's what a hotspots analysis gets for you. The next thing, yeah?
Does vTune run on distributed memory programs, or is it all shared memory?
So vTune specifically is targeted for shared memory, but the way that vTune works is it's made for analyzing whatever's running on a node. So you can analyze multiple nodes at the same time, but it's going to give you performance data about what was happening on that node. So it's made to target, a shared memory process at a time or a node at a time. There's another tool that I have a slide on called Intel Trace Analyzer and Collector, and that's specifically designed to monitor things like MPI weight and all the various MPI communication that could be causing a bottleneck in your application. Yeah. But vTune is specifically targeted at tuning a certain node. Having said that, you might think, well, I have an MPI process, so I'm not really interested in tuning for a certain node. But MPI is running the same process on all those nodes, right? So if you can tune whatever's happening on one node, and that same thing is happening on a million other nodes, that same performance tuning is going to affect all of those nodes. So don't, put off single node performance tuning just because you have an MPI application. In general, they're all doing the same thing or very similar things on all of the nodes. Yeah.
It means that you have to submit your job and then to log in various nodes to actually see what's going on.
If you were going to use vTune for that sort of thing, yes. So what you probably would do is you would not be profiling every rank. You would assume some subset of ranks is representative of your application. You would profile them. And then you don't actually have to log into that node to do the analysis. It just creates a result file. You can copy it back to your laptop and look at everything on the GUI on your laptop. So that's the other thing I'll say about GUIs. Yeah, your cluster, at Argonne probably doesn't have the GUI available to you, but you can do the analysis there, copy the results back to your Mac or whatever, and look at it there, right? Yeah. So that's another kind of plug for GUIs. Is that's why these big clusters, right? They don't have GUIs, so a lot of people don't use GUIs, but there are tools out there that don't require the GUI to be on the machine where the analysis was done. So once you've done some hotspots sort of analysis, the next thing you want to do is look at resource utilization. You've paid for these nodes. Make sure you're using them, right? How are you using these nodes that you've reserved, and how are you using the memory connected to those nodes? Is your application parallel? Is it parallel enough? If not, you're going to be leaving a lot of hardware on the table. You're not going to be using all the cores available to you, and that's pretty much just a waste, right? You want to be using all of the cores available to you. There are a few use cases and people that I've talked to that have applications that, I want my application to only use at most 35% of the machine because I need to be able to handle heavy loads from customers when they come in. And that is a use case, but in general, I would say probably most people in this room aren't really interested in keeping utilization down. If they can use the available hardware to make their application run faster, right? You don't want to waste it. You don't want to use it and put idle threads spinning over there. But if you can use it to make your application run faster, most people in this room would probably be interested in that. You can take advantage of hardware using multi-threading like OpenMP that we talked about. You can also take advantage of it using something like MPI. You can run an MPI rank on every core of the machine. And you can do some mix of both, which most people are finding is the ideal solution for them. And I'll talk a little bit more about that. Are you memory bound? Is the reason that your application is running slow on a node because you're maxing out the memory bandwidth? And these kind of things are the things that you can get from various tools. This is just top, right, which everyone should be familiar with. You can see, what's the CPU utilization on the node. You can see how much memory is being used. And this will give you a general idea, right? You'd like to see the CPU utilization at 100% if you have, enough threads to take advantage of all the cores. But from there, it's not really telling you too much about what to do next, right? It'll tell you, yeah, you took advantage of the machine, or no, you didn't, or yeah, you're using up all the memory, or no, you're not. But it doesn't exactly tell you what to do next. For that, you'd like a little bit more detailed analysis. And here's one reason that I'd like to try and convince you that GUIs are useful. Here's actually showing the dynamic runtime of an application and what was happening on various CPUs over time. It's not just giving you a summary at the end, right? And you can actually visualize your application, which will teach you a lot about it that you wouldn't have got otherwise. Here's a CPU usage histogram that's showing how much time was spent using all of the cores on the machine, on a 4-core machine, how much time was spent using only 3 of the cores. And this kind of detailed information leads you in the right direction of determining whether or not you're using all of the CPU resources. There's also some information here about how much overhead time was spent in various threading libraries and that sort of thing. But by getting this detailed analysis, you really have the ability to focus where you want, right? If you were just looking at top, you would have no idea where to go. Here, you could actually zoom in and say, okay, here's a region of really low concurrency. Let me zoom in there, see what function I'm running, and figure out, why was I low concurrency during function foo? All my other functions had high concurrency, but this one function didn't. From something like top or something like some print statements in your code, you're probably not going to get that information. In addition to knowing whether you're taking advantage of all the cores, you'll want to know whether you're memory bound. So you want to know, what is the max theoretical memory bandwidth on a node? And there's a really simple calculation you can use, based on the speed of the RAM and that sort of thing, to get your max theoretical bandwidth. And then use some sort of profiler to determine, how am I actually using that bandwidth over time? Is it getting really close to the max theoretical bandwidth? If so, maybe I should look at relieving that pressure on the memory. And so I can, fork off, if you have, 2 stages in your application, read from memory, then compute, read from memory and compute, and all your threads are in lockstep between those 2 stages, it's really easy to max out the memory bandwidth. But if you could stagger those, the memory and the compute, you might be able to relieve some of that pressure. For multi-socket systems, this becomes equally as important because you have, in theory, memory bandwidth for each socket, but depending on how you schedule things, you can really shoot yourself in the foot with memory bandwidth. This is a screenshot of the Intel Trace Analyzer and Collector tool that I talked about for profiling MPI applications. It's interesting, a lot of the thread level parallelism issues like synchronization and data sharing and that sort of thing that are introduced with thread level parallelism are also introduced in some form within MPI or multiprocessing. And it sort of just shows its head in a slightly different way. Here, we're doing an analysis of some MPI communication, and it's showing you, where are you waiting for someone to send you data, and how much time is being wasted in all of those waiting states. I don't want to get into too much detail about ITAC in particular. There's also a lot of tools that can do this, but MPI communication can be a huge barrier in MPI applications. You can't just assume, oh, I need to send this data to this guy. When he gets it, he'll move forward, and everything will just, go along swimmingly. If you do that poorly, you can be worse than a serial implementation. If your communications are in such an order or fashion that, 90% of your threads or 90% of your processes are waiting on one guy because you've written it in such a way that he's the only guy with the good data, a tool like this will be invaluable in showing you, hey, yeah, you have MPI, and maybe even all of your processes are taking up CPU time, but the CPU time is basically a spin weight for the data to come in. And you wouldn't get that information just by looking at wall clock time. So what's next in the application tuning phase? So look at your hotspots. Are your hotspots common algorithms? If so, look for optimized libraries. None of us talked beforehand about these presentations, but we all seem to hit on optimized libraries, right? That's the lowest hanging fruit in this kind of situation. If you can find someone who's vectorized and tuned your matrix multiply for that platform, for that hardware, for that new hardware, and you can just plug that in, that's going to be better than what you could write by hand. I don't want to go out on a limb and say that nobody in here can write the best matrix multiply, but the guys that do that 8 hours a day, 5 days a week, they're going to write a better one probably. If your hotspots are not in common libraries, then start looking at things like compiler optimizations. This is kind of in the order of how much work is really required. If you can throw a compiler switch to optimize something, maybe it works, maybe it doesn't, but it's pretty low-hanging fruit, right? So start looking at compiler optimizations, what can be done. James talked about some of the vectorization that's available in the compiler. You will need some expert analysis if you're moving on. If the compiler's not working, you'll need some expert analysis to start looking at the algorithm and how it can be refactored. This is obviously the opposite of kind of low-hanging fruit. This requires someone who knows, hey, it's okay if we do that loop before this loop. Hey, it's okay if we pull that calculation over here. But if all these other things haven't worked for free, then you're going to have to start doing some algorithm analysis. And then after algorithm analysis, that's when we recommend you start looking at hardware performance. How are you actually using the transistors on the chip and the new features? Is it efficient? If you've determined that your system is underutilized by looking at the resource utilization analysis, that's when you want to look at how can I use those resources. If cores are idle, I need to add parallelism. That can be MPI, that can be OpenMP, that can be TBB. There's a lot of ways to add parallelism, but take advantage of those cores. If you are underusing memory, that's not necessarily a bad thing, so I won't say make sure you're using all of the memory, because if you're just using caches, that's much better. But if you're saturating the memory, start thinking about how you could use that a little bit less. So tools really help you identify where to look. And when you want to go to these extreme scale sort of applications, putting in your own sort of timings really isn't the most efficient way to do performance tuning. Some tools do suggest specific fixes. Some of the slides I have a little bit later show you here's an issue and here's how we suggest you fix it. There's not always a silver bullet to tell you exactly how to fix an issue, but at least pinpointing the issue is made a little bit less painful by using tools. And in the end, there's no silver bullet. The developer will have to make changes if these other sort of easy things didn't work for you. You are going to have to spend time designing your algorithm to make sure it's correct, but if you want to scale to these huge numbers of cores, you're also going to have to spend time making sure your algorithm performs. The last level is the microarchitecture tuning level. It used to be that this was only for architecture experts. You needed to know exactly how those transistors are hooked up on that chip to get software to run well on it, or to do tuning at this level. But with the introduction of tools, this has been abstracted away. People that are just regular software developers can do tuning now to take advantage of the newest features on the newest hardware platforms. So this has opened up a lot of opportunity for performance. So how do you do this? Well, you use architecture-specific events. And when I say architecture, I mean Intel-specific events. And actually, each Intel platform has specific events. And I know, for example, the Blue Gene, the architecture that it's built on, has its own events, right? And you'll have to learn a little bit about the architecture in order to do this kind of tuning. The best way to do this is to use predefined metrics of those events, which people that are experts on the platform have already defined for you. I'll talk about this a little bit more. Use tools. You don't want to be doing this kind of thing without a tool. If you were doing this without a tool, what you would do is you would write a driver, you would count these events, and your driver would tell you, hey, there were 65 million cache misses, the end. Now what, right? So use a tool that abstracts this away. Linux Perf, which is built into the Linux kernel, has the ability to collect these events and create metrics. vTune, which is Intel's tool for Intel platforms, has the ability to do this as well. Linux Perf is a cross-platform tool. It's not Intel specific, so you can use Linux Perf on other platforms as well. And at this level, unfortunately, we've used the same name twice. We have a top-down characterization of the microarchitecture as well, which is different than the top-down that I'm talking about overall today. But there's a very specific way that we recommend doing tuning for the microarchitecture, and it's called the top-down characterization to locate the hardware bottlenecks in your application. There's a white paper online that describes it in detail. Just to call out, we're getting into Intel-specific tuning here. So at the microarchitecture level, you're doing tuning to run on a specific platform. Although the changes that you make will often make you run faster other places as well. The way that these events are counted is by using something called a PMU, a performance monitoring unit on the hardware. There's a register on an Intel chip that counts things like cache misses as they occur. It counts when your branch mispredictor mispredicts a branch. It counts whenever you access the memory. And this is really low weight, right? Because it's actually a register that's just counting. It doesn't have overhead when it does that. And by counting or sampling these events, you can get an idea of where these are occurring. However, if you were to just write your own tool to look at these raw event counts, they'd be very difficult to interpret. This is what they would look like if you just, it wouldn't even have a GUI, it would be text. And it would just say there was 65 million L1D mispendings. There was 52 million, cycle activity, this event. And that would be really hard to do anything with. But by using metrics with documentation, you can combine them into very useful numbers about where is the bottleneck of your application and what can be done with it. The last slide I have for the introduction is talking about adding regression tests to your performance. I mentioned this when I talked about looking at the various levels of software design and think about performance throughout. When you have tests for your application that you run to make sure you're getting the right answers, also add tests to make sure that you're performing up to snuff. Take a baseline to see how long it takes you to do something. After you make several code changes, have a test that takes that same measurement and compares the two. This is pretty easy to automate with scripts these days, even if you're just doing some basic timing code. But if you want to scale to these large machines, you can't let your performance, get out of hand negatively as you try and, fix your algorithm. You need to keep tabs on that regularly. It's too late after you've been working for 6 months. Then you find out, oh, it's slowed down, 100 times. Okay, is there any questions? Yeah.
Are there any open source or educational licenses for vTune or any of the Intel performance?
So there's evaluation licenses, there's academic licenses, and there's also student licenses. There's several different ways to license it. Some are less expensive and some are free, depending on the setting. I'm not a licensing expert, but if you look online, there's different ways to license it. It's not just all commercial licenses. All right, thanks everybody.